So this is lecture 30 supplementary, a couple of topics that we could not discuss today, so we'll talk about them in this supplementary recording. So the first thing I want to talk about is relative velocity, of course for a motion in a plane. So if you have an object moving in a plane which can do both translation and rotation, so in that case, let's say this is our object. Okay. So this is translation. I was trying to show rotation here. It seems that will not be possible. So let's draw it again. So I'll try to draw as similar as possible. Okay, so let's say this is the same object. Now we have points A prime and B prime which have moved. So in this case, the displacement of point B we call delta R for B, and similarly displacement for point A we'll call delta R for A. And this vector from B to A is the vector R. That's what we are calling it. And that's this time we have the vector. Well, let's call this as the vector R from B prime to A prime. And what we can see is that the vector R, let's call it R A prime with respect to B prime. Okay, so R A prime with respect to B prime is, if we look at these vectors, so let's copy delta R B with a different color this time. So this vector, that's the change delta R A with respect to B. Let's write that one. So this is equal to, if we can see from here, delta R A minus delta R B. Okay, and if you differentiate sides with respect to time, so delta R A changing with respect to time is nothing but the velocity of A in the limit that delta T tends to velocity of B A, sorry, and this is velocity of B, that's delta R B by delta T in the limit delta T tends to 0. And on the left hand side we have V A with respect to B. So if it was a pure translation, then what we see is that V of A with respect to B will be 0. because in a pure translation you will see that A and B, well, VA and VB will be the same. But if it is not pure translation, if there is some rotation in it, then we'll have this VA minus VB equal to VA with respect to B, and then that is because of rotation, because it's a rigid body. So with respect to, let's say, point B prime or point B, if you're sitting on it, then you cannot see that A prime can go away. The distance will remain the same. So RA prime with respect to B prime, this thing, magnitude, is going to be constant. So if we have only rotation that can happen, so this can be written as omega cross R A with respect to B. Okay, so this is for a rotating vector. And if we take the rotation, I mean if we take the motion sitting on A prime, then again omega is still the same, because omega is a property of how much rotation the body is experiencing, and R B with respect to A is simply minus R A with respect to B. So we can write V B with respect to A is simply omega cross R B with respect to A, that is minus of VA with respect to B, that is expected. So this allows us to study motion relatively from one point or the other when the body is rotating and translating. So translation effects are removed, only the rotation effects matter when you take relative velocity, relative motion. Okay. Similarly, acceleration. So acceleration of A with respect to B is, there is a normal component and there is a tangential component. So the acceleration in the normal direction is omega cross R. Okay. R here is R AB. Let's write that, plus alpha cross R. Okay, so these we had written in the main lecture today, where we wrote the acceleration in the two components. Okay, so the same is true for a situation where this is basically a motion with translation and rotation, but since you're sitting on one point of the body, it appears to be a pure rotation problem for us. Okay, so with this idea, let's talk about motion relative to a rotating axis. So in this case, even though we're talking about a rigid body, what we'll do is we will write the expression such that it is true for point particles, collection of particles, and we'll take two arbitrary points. So in rigid body, these are two arbitrary points on a body will not go away from each other, but here they can, doesn't really matter. So we have a capital XY axis with an origin O. So this is a non-rotating axis. And then we have a point B, from which we are trying to understand some motion. So basically there's an axis attached to B. Let's use a blue color. Oops. So this axis denoted by small xy this small xy is is a rotating axis. And let's say it is rotating with some omega. Okay, so the position vector of B is RB, and we take some point, some point A, so this vector from the point B to A is R A relative to B, and then the vector from the origin of the capital XY axis is given as RA. Okay, so we can write RA as RB plus the relative RA relative to B. In this case, now R A relative to B will be measured in the small xy axis. So let's say we measure it as xi plus yj. So I and j in this case are unit vectors in the small xy axis. Okay. So if in capital axis we have unit vectors as capital I and capital J, then small I will be some function of capital I and capital J, and so on, so as small j is a function of capital I and capital J. Okay, that's what the meaning of a rotating axis means. Okay, so small x and small y are the coordinates of point A, capital A, in the rotating xy axis. So let's differentiate this with respect to time. So we have RA dot is RB dot, and then we differentiate x I hat plus y j hat. Now see that in this case we get additional terms as well. So there's a plus here. So we get, first we get x dot I hat plus y dot j hat, these terms, and then we have a set of term where we have the time rate change of the unit vectors small I and small j. Now this x dot I hat plus y dot j hat is basically the relative velocity that is of A, that is measured in the small xy axis. So in the frame that is attached to B, the person who's sitting in that frame and measuring the movement of point A will measure as V del. They'll measure the rate of change of x and y coordinates. But of course that's just this part, and then x times I hat dot plus y times j hat dot is definitely non-zero, because I hat and j hat are rotating vectors. And we can very easily see that we can write I hat dot as omega cross I hat, and j hat dot can be written as omega cross j hat. Okay, so that's a rotating vector. So I hat is a vector that does not change in magnitude, can only rotate. So it di by dt simply becomes omega cross I. We discussed that when we talked about the vector nature of omega. Now R A dot is simply VA, RB dot is VB, and then we have the relative velocity component. And now here what we can do is we can write this as omega cross, and then we have xi plus yj. And remember, xi plus yj was nothing but R A relative to B. So what we see is VA minus VB is VREL times omega cross RAB. So VA minus VB is simply the relative velocity of A with respect to B in the capital XY frame, and VREL is the velocity of A with respect to B in the rotating small xy frame, and omega cross RAB is simply there because of the rotation of the axis small xy. So in fact there is a general expression for vectors seen from one axis or the other. So let's write that. So in general we can write dA by dt, where A is a vector in the capital XY frame, that's the fixed frame, is equal to dA by dt from the small xy frame, that's a rotating frame, plus omega cross A. That exactly is what this is. In this case the vector A is a relative vector joining from B to A. Okay, so this was velocity. Let's talk about acceleration as well. How do we link the acceleration of a point if it's measured from a rotating axis? So the acceleration of the point A is simply the derivative of the acceleration. So we are starting with A. So using A, so we differentiate, let's say differentiating A. So we get acceleration of A is acceleration of B plus, now we have a V relative, so the derivative of that, time derivative, and then we also have omega cross RAB. So when we differentiate that with respect to time, we get two terms. The first one is omega dot cross RAB, and the second one is omega cross RAB with a dot. Okay, so let's look at different terms. So let's call these. So this is 1, this is 2, and this is 3. So let's analyze. We'll start with 3. omega cross r dot AB. Okay, so let's see what omega cross r dot AB is. Now r dot AB was this term, because r dot AB dot was simply VA minus VB. So this has a term V relative plus omega cross RAB. Okay, so this we can expand. So this is the term number 3, which had omega cross R A to B. So let's go to other terms. Let's go to term number 1 now, which is the derivative of V rel. So remember what was, let's recall what was V rel. So V rel was the velocity that was measured in the rotating axis. Okay. So this contained the derivatives of the x and y, the positions in the rotating axis. So if we differentiate that with respect to time, again we get these terms, which are second derivatives of x and y, plus we also have a term, we have terms which are because of the derivatives of the rotating vectors, like this. So this first one is nothing but A rel, that's the relative acceleration that's measured in the small xy axis with the origin at B. So relative acceleration of A with respect to B in the rotating axis. And the second term, now I dot can be written as omega cross I, and j dot can be written as omega cross j. So this basically becomes omega cross, and then we have x dot I hat plus y dot j hat, so that is V rel. Okay, so that is the time derivative of the relative velocity V rel. Next we'll see what happens to term number 2. Well, term number 2, there is nothing that we need to talk about. It's simply omega dot cross r. That's because of the change in omega. For two-dimensional motion, that is simply angular acceleration. Well, this is simply increasing in the omega or decreasing in omega, and that's the angular acceleration term. So let's write now everything in the acceleration. So we see that well, this omega dot cross RAB was this term, and then we had omega cross R. So that was coming from the omega cross R dot, R dot, this one. Okay. Next we have the omega cross V rel, but we had two of these, one coming from term number 3, the other coming from term number 1. So we add them together, and then the last one is the A rel term. That's this one. So this is the acceleration of A with respect to B in the capital XY frame. So there's lots of terms here. So let's understand what they are. So this omega dot cross RAB is because of the tangential acceleration. So that's the tangential term. You can also visualize the directions of these terms. Okay. So if this is our body, this is the point around which we are measuring. This is B, this is A. So let's say the body is rotating around B. So this is RA with respect to B. So omega dot is, so this is a two-dimensional motion. So omega dot is also in the same direction as omega, that's outside the plane of paper. So omega cross R gives us this direction, which is nothing but tangential direction. So that's what we have. Now let's look at the second term. This is omega, so omega cross R gives us a tangential term. Then if we take omega cross that term, so omega is outside the plane of paper, crossed with the tangential term, that gives a term in the negative R direction. So that's the centripetal acceleration. And then this third term, if you recall from the first week of lecturing, this is the centrifugal term. I'm sorry, this is the Coriolis acceleration. Please excuse the error. So this is the Coriolis acceleration. And then finally we have the ARL term, which is simply the relative acceleration that is measured in the rotating frame. This is a pretty intense expression that we have here, because this allows us to calculate the acceleration of a point A with respect to a point B if you are sitting in rotating frame. Because till now we always had an inertial frame, but if you have a rotating frame, which is a non-inertial frame, you can calculate the acceleration, because ARL is basically measured. So this is the acceleration of A measured in B, measured from XY. Small xy frame. Okay, so in small xy frame, all you see is the double dot of x and double dot of y. So this is the relative acceleration. And then everything else is because of the rotation of the frame. So all the other terms have omega in it. Okay, so just to reinforce our understanding of this expression, which is actually quite a useful one, let's box that. Let's solve a problem. In fact, we have already solved this problem in the beginning of the course, where we had a tube in which you had a mass. The mass was connected to a string, and the string was rolled over a spool. And in this case, what was happening was the whole tube was rotating counterclockwise with omega, and also the spool was rotating with omega naught, and the spool radius was b. So what was happening was that as the spool rotated, it resulted in the mass moving outwards in this tube. So we had to find what are the radial and the or what is basically the acceleration of the mass m in this case. So this is mass m. Okay. So when we applied the polar coordinates, let's recall that. So we said that A will have two components. One is along R. So this is your R hat direction, and there was a theta hat direction which was perpendicular to the tube at any instant. So this is AR, and A theta is what we had to calculate, and that's enough. So AR is R double dot minus R theta dot squared. R double dot is 0 because we are controlling the motion of the string in such a way so that it moves so that R double dot is 0. R dot is actually constant in this case, which is omega naught times B. So this is 0 minus R, and theta dot is simply omega. So that was minus R omega squared. And A theta, which has two terms, 2 R dot theta dot plus R theta double dot. So R dot is a constant, which is B omega naught, and theta dot is also constant, which is omega. And the other term, which is R theta double dot, is 0 because theta double dot is 0. Okay, so this comes out to be 2B omega naught times omega. Okay, so this was the expression that we had got earlier. Now what we'll do is we'll try to apply the rotating coordinates system that we have. So we'll calculate the acceleration of the mass m sitting in a rotating coordinate system, which is rotating with omega at B. So A of B is 0 because in this case there is no acceleration at the point B. B is actually at the origin. So this becomes 0. And then we have the different terms. Now omega dot is 0 because there is no angular acceleration. So this omega, the relative tangential acceleration term is 0. And then we have the centripetal acceleration term. This will not be 0. So we have omega cross r. Okay. So let's look at this. So omega cross r, omega is along the z axis and r is along the r hat direction. So that comes out into the theta hat direction. And when you do omega cross omega r in the theta hat direction, that becomes in the minus r hat direction. So we get a minus omega square r in the r hat direction. Then we have the Coriolis acceleration term. Now VREL, if you are sitting on the rotating frame, all you see is that the particle goes out. So VREL is simply a constant which is equal to B omega naught. And when you do omega cross the direction of VREL, what we get is the theta hat direction. So this is 2B omega naught in the theta direction. There is an omega as well. Okay. And then AREL is 0 because if you are sitting in the rotating frame, you will see that the mass is going away from you at a constant speed. So this term is also 0. So we see that the acceleration of the mass is minus omega square r in the r hat direction and 2b omega naught omega in the theta hat direction. This is exactly the same as what we had got using the initial discussion. Good. So that basically allows us now to evaluate a problem sitting in any frame. You can sit on the ground frame and calculate AR and A theta, and no problem, or you can also use these expression that allows you to evaluate a problem from a rotating frame. It's your wish, but I'll suggest you try both to get used to using a given approach. Okay, so let's again quickly try to understand the expression of acceleration and see and just to develop an intuition of the expression, the terms. So let's take the example of a circular earth. So let's say earth was a disk. Okay. We don't really need to call it a circular earth. It could be a disk sitting on a disk. So it's basically a circular frame. So in this case you have the center B and you have a point A that you are trying to understand. So if A, so basically what we are doing is we have the disk moving around B at omega. So that's like the problem we had where we had the rotating frame around B, and then we have a fixed frame capital X capital Y. But what we have done is we have moved the fixed frame at B as well. So there is no sort of RB in this case, that is 0. Okay, so in that case we don't really need to draw these things, so I will erase them. Okay, so this is a disk rotating with omega. And point A is fixed. Now earlier we had A rel, so that means meant that V rel and A rel were there, so that meant that the point A was moving. But in this case, let's say the point A is fixed. So if I calculate the acceleration of A, absolutely, and there is no acceleration of B, so that term is actually gone. So what we have is, let's look at the full expression. So AB, the first term is 0, and then omega dot cross RAB, that's a tangential acceleration term, that will be there. The centripetal acceleration term will be there, but then the Coriolis acceleration will be 0 because there is no V rel, point A is fixed, and so is A rel 0 because the point A is fixed. So all we have is, we have the tangential acceleration and we have the centripetal acceleration. So what we see is that the tangential and the centripetal terms have nothing to do with the movement of A on the earth. Okay, I mean this circular earth. It is simply because the earth is rotating with omega around its axis. So these tangential and centripetal terms appear because of that. But on the other hand, the other two terms which do not appear, the Coriolis term and the relative acceleration, they are there because of the movement of A on the surface. Okay. So one must develop this intuition that even on the surface of earth, if a movement of something happens, because earth is also rotating actually, we were simplifying it to a 2-dimension for now. So the rotation of the earth, if you analyze a problem from the rotating movement of earth, so you measure A rel and V rel of a particle, but actually if you want the actual acceleration of the particle, you will have to include the tangential and the centripetal terms which appear because of the rotation of the surface of earth. And of course Coriolis also is there because of rotation, but that also requires the point A to be moving. In fact, if the earth was not rotating, if it was fixed, then A rel would have been equal to the acceleration of the particle A. So it is because of the rotation we have the extra terms coming into the picture. Okay, so one last discussion point here, which is called the instantaneous center of zero velocity. Well, you already have an idea of this from the rolling without slipping situation. And the bottom point, the contact point, is instantaneous center for zero velocity. So the idea is that all the lines rotate with the constant omega. So we discussed that today, that all lines on a rigid body rotate with same omega. So if that is the case, if I have at some instant I have a body and I have 2 points, so let's say point A has a velocity VA and point B has a velocity, let's make it a slightly smaller velocity, VB. So what happens is, if I draw a perpendicular to VA and a perpendicular to VB, what we'll see is that they will intersect. And given that all points have the same omega, so we can write VA as some omega times RA. So this RA is this distance. Okay, and similarly we can write VB as the same omega, because this idea of the same omega times RB. So this is RB. Okay, so this omega is we can locate the center, and the body seems to be instantaneously at that instant the body will seem to be rotating around this point. Let's call it C. Okay, and what is the use of all this? The use is that remember, when we applied the torque expressions, we said that if we have a fixed point, then the torque about a fixed point O is equal to the time rate change of the angular momentum about the fixed point O. So that helps us because we can also apply this about point C, because point C is physically not a fixed point as such, but instantaneously the body seems to be rotating around that point. So that point can be considered as a fixed point, even though that point may not actually lie on the body. So if the body was extended, point C could be appearing, the body could be appearing to be rotating about that point C around which the body was pivoted. This can be a useful idea called the instantaneous center for zero velocity. So that's good enough for the discussion. So we are at this brings us to the end of planar rotation motion. Okay, so the next topic is going to be on three-dimensional rotation of rigid, or three-dimensional motion of rigid bodies. Thank you.